Okay, is that coming through?
Yes, it is.
One sec.
And may I record this session? Is it okay with you?
Yeah, that's fine.
Thank you.
All right, cool. So I'm Ratnaksha. I'm a researcher here at iHarp. And so this is just kind of a broad overview talk of oceanography or physical oceanography in particular. And it's a pretty broad topic, obviously, because people do PhDs and that stuff. So it's very hard to like condense things down into a less than 1 hour lecture. But anyway, I'll try and I guess start here just by talking about what exactly is physical oceanography. So as oceanographers, like people want to study the chemistry of the ocean. A lot of people have ideas about what oceanographers do, which is like talk to sharks and dolphins, but like a lot of climate scientists or physicists, like we were not interested in that. We're interested in kind of understanding the physics of the ocean. How does the seawater move and why does it move? And so the answer lies in then kind of the physical underpinnings of fluid mechanics. And so we use a lot of different kinds of tools. So we use satellite measurements, in situ measurements. Some of these are like kind of shown in these pictures. And then some sort of simplistic or mathematical models of the dynamics of fluids to try and kind of piece together what the dynamics of the ocean look like and why does it move and what affects the motion of it. And then kind of the broader picture of that understanding is to be able to explain or understand kind of how the dynamics of the ocean affect the biology of it and also the physical chemistry part of it. And also then kind of more global scale, we're trying to understand how it impacts the weather system and the climate system and how it's evolving over time. And so like that's kind of the broad understanding that physical oceanographers are trying to bring to the field. And we're using lots of different tools, as you all probably know. So my training was in observational physical oceanography. So I come from more trying to understand it from using observations from in situ data like ships and these floats that are, just thrown into the water and they communicate via satellite. And so they're making these physical measurements of the properties of seawater that help us to try and understand that. And then we obviously use computational methods and numerical methods to try and solve equations of motion of the fluids to try and be able to like capture all of those dynamics together from these measurements. And so this is like just another kind of an artistic plot, but it's just a sea surface temperature illustration from a satellite. So this is basically the coastline of the US. You can see Florida there, and then kind of Chesapeake Bay, and then the rest of the North American East Coast coastline. And then what you're seeing is that just this kind of the gradient in sea surface temperature. So this is a satellite view of what sea surface temperature might look like in a particular day. And so you see like the Gulf Stream and some of the meanders and eddies and mesoscale eddies that form as it like interacts with the coast of the US, and then it transforms into a slightly different current as it moves along in the North Atlantic. And so like you see not only this northward transport associated with the Gulf Stream, but you also see other filaments and meanders associated with the sea surface temperature field from the satellite image. And so this, the field of oceanography goes back, maybe hundreds of years. So this is like a map of North America from like Benjamin Franklin's time. So this is 1700s, late 1700s, and this is North America. And then they have like this kind of schematic of what the Gulf Stream might have looked like back then. And so, they're not really all that far off in terms of kind of their understanding of what maybe the Gulf Stream looked like, because they obviously did not have satellites to observe those, right? So they're basically using buckets of water to try and measure temperature and try and piece together maybe what the Gulf Stream even was, right? So it goes back hundreds of years, but like it's gotten more and more sophisticated as time has gone on, obviously. And so like to like distill it down to like very simplistic view of things. First of all, like what are we talking about when we're talking about temperature. So like this is just a figure kind of showing you what a sea surface temperature field might look like globally. And so, there's this distribution of temperature that exists in the along the sea surface along the globe, right? So, you see this redder means, higher sea surface temperatures in the equatorial regions, and then you have this gradient going northward where you have like slightly colder and colder temperatures as you reach kind of in the polar regions where you have very cold waters, obviously, and you can understand that it has something to do with the difference between incoming solar radiation, outgoing long wave radiation, and so we covered that in Dr. Zhang's lecture last time around. So I kind of just put this on, but we'll go into more detail about this also again. But the big picture thing is that you have this surplus of incoming solar radiation at the equatorial regions, and so you have this warming that occurs in the sea surface temperature field. And so like you see 28, 30 degrees Celsius contours here in the equatorial regions, and as you move northwards, you have this deficit that occurs as you move northward, and so you see a loss in surface heat, and so that generally lends itself to colder temperatures, and so you see that in the colder regions there. And so what does measuring temperature look like in our field? So this is probably one of the largest data sets that we have as far as measuring temperature goes. Like I said, people have been measuring this stuff in buckets back in the 1600s and stuff. There's records of people measuring stuff, and obviously it wasn't all that sophisticated back then. But yeah, there are still records going back to medieval era and Renaissance time where people have taken temperatures, and so this is like one of the most fundamental measurements that oceanographers or seafarers have made. And so this is probably our best resolved, longest running historical record wise understanding of one of our climate indices or oceanographic variables. And so they used buckets back then, but now in 1900s to 1970s, they use mercury thermometers that kind of look like this in this figure. And then there's more sophisticated measurements now, like with thermistors and more electronically calibrated measurements that can be made with using these temperature depth sensors, conductivity temperature depth sensors. So this is what probably you would find in any modern instrumentation that's measuring temperature in the ocean. And then obviously we started using satellites in the 1970s, where you have these satellites that are orbiting the Earth, and they have microwave radiometers or something that basically are bouncing pulses back and forth between the satellite and the Earth, and that tells you something, the reflectivity or the interference with the water will tell you something about the temperature. And so these satellites have these sophisticated instruments that are able to measure temperature also. Okay, so temperature, and then there's, so we're interested in salinity. So these are like two very important variables, and it sounds kind of kooky when you're just talking about some salinity and temperature, but that basically determines the motion of the fluid because it governs density, and density, then you can take that to the next level. We'll talk about it if there's time, but so yeah, salinity is measured, I guess very simply, is just the mass of salt that's in a given volume of water and a given mass of water. So that's called absolute salinity, and it's expressed in grams per kilogram, or practical salinity units, it's also called. So you'll see a lot of measurements that are PSU. And so this is basically just the grams, weight of salt in grams per kilogram of water, so parts per thousand, and salinity. And so it's pretty useful measurement. And then there's very small variations in salinity that happen, and so this is very interesting to chemists and stuff, but also to oceanographers, because it does affect density to a great extent. And so we're interested in making these measurements of salinity. And so when you look at salinity, what are kind of the constituent salts? And so there's basically a large amount of sodium chloride, which is common salt, so that's what you probably expect. And then there's a bunch of sulfates and magnesium sulfates, magnesium chlorides, potassium and calcium, and then there's some trace salts, which are about less than 1%. And so typically sea surface salinity is, the variation is very small, like I said, but people are very interested because it does control density for second and third order. And so like a lot of the density is governed by temperature variations, but like salinity is also important. And so the range is 34 to 36 grams per kilogram or PSU. And then there's a bunch of different constituents, like it's shown in this pie chart. And so the average ocean salinity is about 34.9. And so as far as surface salinity goes, again, so we looked at surface temperatures and now looking at surface salinity, you can kind of see this also global map of what that might look like. And so you see, like I said, like the salinity variations are small. So you see the values here are between 34 and 36 generally, right? So you'll have, saltier waters in the Atlantic, and we don't have to necessarily go into all of the details about why that is, but there's processes. I guess I do have a couple of slides, so we'll chat about it. But there's this variation in salinity. So like you see this Atlantic basin having a lot more saline water compared to the Pacific Ocean or North Pacific of the coast of California is a lot fresher in comparison to it. And then there's, you might also see like the equatorial regions are more salty than say the polar regions. And so like the regions around the polar regions, like the Arctic Ocean and Antarctic and the Southern Ocean are fresher compared to the equatorial region. So you have this north-south gradient also, and then also variations between the different ocean basins. So like I say, yeah, so what sets salinity? So it's basically the total amount of salt, dissolved salt in the oceans is constant, you can imagine, like on large time scales of millennia or longer. The amount of salt is considered to be constant. You're not really adding anything. So the amount of dissolved salt is constant. And so then why are these gradients being formed? And so you can imagine, so there's precipitation that happens. So rainwater falling in the ocean is going to add fresh water to it. And then there's river runoff. So you have all these different rivers that are discharging a bunch of fresh water into the ocean. So those are two important inputs that are providing fresh water. And then you can subtract the evaporation that happens. So like the sun is shining on the ocean surface, and so you can expect that there's a bunch of evaporation that's going to happen also, right? So that balance between how much fresh water is falling into the ocean and then how much is getting evaporated basically tells you where it's going to be saltier versus where it's going to be fresher. And so you can see that in the Atlantic basin, like I said, so there's more evaporation that happens compared to how much precipitation that's falling. And so you see these positive values that denote a net total a freshwater deficit. So that's basically a net positive freshwater deficit. So you see like more evaporation happening compared to how much precipitation and runoff is occurring in the Atlantic Ocean. And so similarly, you see that in most of the equatorial regions. And then when you compare that with the high latitude polar regions, you see that in the Arctic Ocean and stuff, you have more precipitation and runoff compared with how much evaporation is happening. That's probably more intuitive because like you have not only precipitation happening, but also the temperatures are very low, so you have less evaporation that occurs. And there's a lot of freshwater runoff from big rivers that occurs in the Arctic Ocean. So you have a kind of a accumulation of fresh water that happens in the polar regions as compared with the amount of evaporation that's happening. So you have a net freshwater input into the regions. And so I guess what you can do is now you can again look at the sea surface salinity map here on the right and then compare that with the patterns that you see in this precipitation net runoff, net freshwater input or export. And so you will see that these patterns align quite well with the pattern in sea surface salinity. So that's basically what sets it. So you have increase in sea surface salinity, in kind of the equatorial regions, and so you basically see that, and there are slight differences that occur in different regions, but that's that's not the focus of this talk. But yeah, to a large extent, first to zeroth and first order, that pattern generally matches up pretty well. Okay, so as far as talking about salinity measurements, how do we do it? So the simplest and oldest way is basically evaporate a bunch of seawater, and then you can just weigh the salts, and that's it's obviously not how scientists will want to do it because it's very energy intensive. But I bet back in the 1800s or before that, people did that because that's probably the only way that they had how to do it. And then there's other titration methods that are available that you can determine the amount of dissolved chlorides or bromides or iodides. And so, but that is also very cumbersome. And so I think there's modern tools like these conductivity sensors that are able to measure that much more accurately, but you just have to be careful that it has to be referenced to a standard salinity regardless. And so there's, yeah, you just have to make sure that the instrumentation calibration is checked and that that it's calibrated. And then you can obviously measure this from satellites also, just like you did temperature. There's these NORS satellites that are measuring sea surface salinity from space. And so that's basically kind of covers temperature and salinity measurements and how they're made. Okay, so now we can look at what the spatial distribution or the spatial distribution of the seafloor might look like. And so you can look at that these are these different ocean basins that we talk about. And I know this is kind of very basic stuff, but you can look at kind of the radius of, so I guess I'm going somewhere with this. So the radius of the Earth is 6,371. That's a good thing to know about for trivia as well. And so when we're talking about the Earth, so like some boilerplate stuff here is that we're talking about latitudes that go from -90 to 90 degrees, and 1 degree of latitude is roughly 60 nautical miles, or about 111 kilometers. And so each of those degrees of latitude can then be subdivided into minutes and seconds, and so each minute is 1 nautical mile, and so you have 60 nautical miles in 1 degree. And so when you're going north-south, we call it meridional direction. And then longitudes, again, there's 360 longitudes, so it's -180 at the date line, which is in the middle of the Pacific, and it goes to 0 degrees as you move eastward to Greenwich Meridian in England, and then goes, if you go further east, keep going into the Pacific from England all the way to the Pacific, so it's -180 to 180. And so the spacing between the longitudes, however, since the Earth is spherical, it's not constant, so it scales as the cosine of the latitude. And so it's maximum at the equators. If you look at this globe, the spacing between longitudes is not this is maximal at the equator, and as you move poleward, you see that the spacing between the longitudes changes. So it scales as the cosine of the latitude, where cosine of 0 is 1, and so that's where it's maximal at the equator. And then as you move towards the pole, it's the spacing gets to 0. So cosine of 90 is 0. So that's basically how that works. Okay, so what does the depth distribution look like when we look at the ocean? So sorry, so this might be a little confusing graph. So this is the elevation. You have the sea level at 0 right there, and so everything above is considered to be on land. Everything below the sea level is obviously in the water. And so you see the mean height above the sea level is about 743 meters above sea level. So that encompasses all of the continents, obviously. And then Mount Everest, the highest point in the land, is about 848 meters. And so that's over there. And so you can see that looking at this histogram, so that most of the Earth, the mean height is 743 meters. And so when you look below the water now, you go from 0 meters all the way down to the deepest point, which is Mariana Trench in the Pacific. And so the mean height there, median, and mode are roughly similar. And so the mean and the median are about 37 to 4,000 meters. And so you can see that most of the ocean is roughly about 12,000 to 13,000 feet below the sea level. And then obviously the deepest point below 8,000 meters roughly corresponds to about 0.04% of the total area of the Earth. And so there are like certain crevices down there in the ocean that are deep and scary, but they don't necessarily cover a lot of the ocean. But most of the ocean still is about 12 to 13,000 feet below the sea level. So it's interesting engineering challenge also to be able to learn and to be able to monitor what's going on deep in the ocean, because it's hard or almost impossible to know that from space, because we're looking at sea surface measurements, sea surface salinity and temperature measurements, but it doesn't necessarily tell you what's going on like deep in the trenches. So that's another reason why oceanographers really want to go out in the ocean and try and measure stuff, because otherwise we can't know what's going on. Okay, so now we can look peer down, and so this is one section across the Pacific. So this is just one line that I've drawn, and this is an actual section that oceanographers will go from Sydney, Australia, all the way to Valparaiso, Chile. So that this is like a 12,500 kilometer section that is measured every few years. And so like this is basically what physical oceanographers love to do, is go out on ships and go take these physical measurements. And so like this is a section, so we're looking at 0 meters, so this is surface, and then all the way down to the bottom. And so what are shown in colors are just the contours of temperature. And so again, at the sea surface, you would imagine that the temperatures are warmer. And so I don't know if you can see what the labels are there, but it's about 10 degrees Celsius or so. And then as you go down to about, say, 2,000 meters, you have these isotherms are about 2 degrees Celsius, roughly. And then deep down at 6,000 meters, the temperature is roughly about it's close to 0, 0.5 or a little lower than that. So that's basically what a depth distribution along a section might look like under the water. And so when you take away the depth distribution, so you have like the continental slope, you have some seamounts, you have some abyssal hills, some mid-ocean ridges, abyssal hills, and so on either side of the continents, you have the continental slope that leads down to the abyss. And then, at every section is obviously going to be different. So this particular section is across the South Pacific, as it's shown in this figure. And so that's basically kind of the bathymetry of what the seafloor looks like. And so the aspect ratio is another thing that comes up in fluid dynamics, and I think I've just pointed that out here. That's the aspect ratio. So the ratio of the depth to the width. So like we're talking about, the depth is roughly hundreds of thousands of meters to tens of thousands of kilometers, and so you can calculate the depth ratio there. And so we'll probably come to what the utility of that is in a bit, if there's time. Okay. And so as far as there's the dynamics of the ocean are concerned, the rotation of the Earth plays a huge role in setting the dynamics. So there's something called the Coriolis force, which I probably won't have time to discuss, but we have this Earth that's spinning around, and so that plays a very important role in controlling how the dynamics shape out for the ocean. And so I think I'm already at 26. Okay, so I'll just probably skip that. All right, so what are so talking about dynamics, if you wanted to like distill down dynamical equations, you could look no further, but you just have to kind of look at Newton's second law. Sorry, what was that? I thought I heard something. Okay. Anyway, so yeah, talking about the dynamics, we could look at the motion of the fluid, and you can distill it down to Newton's second law, which is F equals ma. And so all we're trying to do is basically write out the terms, the different forces that are acting on a fluid. And so what we're saying is that mass times acceleration should be equal to the sum of forces. And so we can write this out in words. You've got some terms that encompass the acceleration term, and then that should equal the sum of forces. And so you can write it down in kind of this mathematical form, and we don't have to talk about this right now, but that's kind of what the momentum balance equation looks like. And so you can see these are kind of hard nonlinear partial differential equations, which we don't know the solution to analytically. So what we have to do is basically solve these equations or simplify them in some way, so that we're able to analytically solve them. Because in its proper form as it's laid out here, we don't have an analytical kind of mathematical solution to it. So what we do is either simplify it, drop out some terms, cancel out some terms based on what problem that we're interested in, the scales of the motion that we're interested in, or what we can do is solve them numerically through to kind of numerically simplify these equations down to something that can be solved by a computer. So the computer will approximate the solutions to these nonlinear PDEs instead of us handwriting the solution to it, because we don't know the solution to it. So they're all approximations to these Navier-Stokes equations. All right, so talking about the scales of motion. So we're going to go through some kind of illustrations of what the different scales of motion we're talking about when we're talking about oceanographic processes, the dynamics of the ocean. You've like the y-axis here is the time scale associated with each of these processes that are given here, and then the x-axis is the spatial scale. So if you're looking at the bottom left part of the plot, you're looking at really tiny spatial scales and really tiny time scale. So like we're looking at molecular processes like diffusion or osmosis, and then there's certain other smaller processes called capillary waves. As you move towards longer scales, so you're going along kind of this axis where you're increasing the spatial scales and time scales, you have certain surface gravity waves, so like wave breaking that's occurring at the beach perhaps. And then there's slightly larger scales such as internal waves or inertial motions in the ocean. And then you're going to larger processes. So now we're looking at submesoscale and mesoscale eddies. And then looking at tidal motions, internal tides and surface tides. And then you're going even larger. So now we're starting to look at what time scales of years. So we're looking at kind of more basin scale processes such as Rossby waves or El Nino events. And then we're moving to even larger, so hundreds of years or tens of thousands of kilometers. So we're looking at more planetary scale processes. So that's basically kind of climate change, or looking at the overturning circulation of the ocean. So these are kind of basically all of the processes that you can probably think of, and then we've subdivided them into like what the spatial scales of motion are. And so this is helpful when we're trying to solve those Navier-Stokes equations that I showed earlier, because we don't know the analytical solution to it. So what we can do is basically look at these time and space scales, and then we can basically simplify those equations so that we are able to compute the solution to it. So okay, so now we can just kind of run through what the scales were, what I just talked about. So this is like the smallest scale. So this is kind of molecular diffusion processes or wave breaking that's occurring. So like these bubble formations that happen like at the surface. So you can see those white caps that occur, and capillary waves that occur on the surface. And so those are kind of the smallest scales that we're considering here. And so like their time scales, maybe the molecular processes are more seconds or a few microseconds, and then whereas these surface breaking or surface bubbles are more time scales of seconds, and then the spatial scales of them are maybe centimeters to meters. Okay, so then we have slightly larger processes. Now we're talking about surface gravity waves. And so this is just kind of a picture of, surface waves that are breaking on a beach. And so their timescales are, their propagation timescales are more minutes to hours, and the length scales are more heights of 1 to tens of meters, but mostly not tens of meters, but they're generally breaking at those length scales. And so this is another picture showing you what a rip current is. And so you have these. So I don't know if folks are familiar with rip currents, but I guess maybe a PSA about how to avoid them, perhaps. So you have these wave breaking chains that occur at the beach. So like you have these sandbar perhaps, or something that's blocking the flow of water, and so you've incredible pileup of water that occurs through these feeders that are breaking the waves. And then what's happening is, due to the accumulation around at the surface along the beach, in order to conserve volume, you have this backflow through the neck and the head that occurs. And so that's exactly what's creating the rip current, is the piling up of water from these breakers. And then you have kind of an accumulation of volume, and then you have some sort of break in the sandbar that allows for that excess piled up volume to get back into the water. And so that's basically the cycle of a rip current. And so what the traditional advice for that is basically, don't try to swim to the shore if you get caught up in a rip current, because as you can probably imagine, that those currents are quite strong. And so what you want to do is basically try and swim parallel to the shore, because otherwise you're just kind of paddling for no good, and you're going to get tired, and people have died because of it. Okay, so now we're talking about tsunamis. So now we're slightly larger time scales and length scales. So like this is an example of tsunami that happened in Indonesia, I believe. And so it goes back to 2004. And so when we're talking about tsunamis, that the time scales are minutes to hours for the waves to propagate, and depends on like where they're propagating. So for example, this Indonesia tsunami occurs off the coast of Sumatra, but the waves that the tsunami then creates then propagate away for minutes, I guess, if it depends on where the coastline is. But generally, it takes a few hours for those waves to arrive at different points, or different points along the shoreline. And so the time scales again are minutes to hours, and then the height and the length scale. So like we have length scales, the propagation of these waves are hundreds to thousands of kilometers. So you can see like this wave train that got created in Indonesia, then travels thousands of kilometers away to continents far away. So tens of thousands of kilometers. And then the heights for these. Sorry, is somebody's mic unmuted?
I think
Anyway.
someone was joining, yeah.
Oh, okay. And then the height is hundreds to a kilometer. So I find that pretty fascinating, that you can have these really destructive waves that you don't necessarily know the signature of the wave until it approaches a coastline, and then it can grow up to a height of kilometer or so, which is crazy. But this is exactly what's happening. So you have these long wavelength. So you have wavelengths of hundreds to thousands of kilometers. And then what's happening when it runs up towards the coastline is like you have the waves slow down, they shrink in size, the periodicity increases, I guess their aspect ratio decreases. And so you have this as it runs up towards the coast, you have shorter and shorter wavelengths, and then due to conservation of volume, you have this incredible swath of water that just comes crashing at you at the shore. And so just kind of a cool animation, just kind of show what's happening with it when a tsunami hits the shoreline. Okay, and then there's so we're moving to slightly larger spatial scales. So now we're talking about internal waves. So these are another, waves that we just saw surface waves and surface tsunamis, but these are internal waves. So they're gravitationally balanced waves, but they're occurring below the surface of the ocean. So now looking at this plot, you have this temperature profile. So you have warmer temperature at the top, colder temperature at the bottom. So that's the temperature scale right there. And then this is like time and hours. So this is, you can see when these measurements were made off the coast of California, you can see like these internal wave signatures in the temperature profile. So this is basically these waves with wavelengths of maybe a few meters or so, and heights of also a few meters. And then these can linger around for hours. And so this is basically what a surface signature of an internal wave might look like. So this is just looking out again off the coast of San Diego. So you can see like these, they're not quite surface waves, but you can see kind of the surface signature of those internal waves that might be occurring. And so that's basically what an internal wave, if you're looking out at a very calm morning where there's no white capping, there's no other surface wave activity happening, but you can see far out and you can see those kind of streaks associated with internal waves. Okay, so moving to some more larger spatial scales. So I showed you this image earlier. So now we're talking about boundary currents, so Gulf Stream or any other kind of boundary current that exists. I mean, we're talking about mesoscale motion, and then so the time scales then we're talking about are weeks to thousands of years, I suppose. I guess if you're looking at longer time scales, and then the height and length scales here are height is 1 to 5 kilometers, because we're talking about the depth of the ocean, and then length scales are tends to hundreds to thousands of kilometers, depending on what boundary current we're talking about here. And then you could go even larger. So now we're talking about more kind of basin scale phenomena. So this is like El Nino and La Nina events. I'm sure you've heard that term before. So this is basically kind of the warming of the equatorial Pacific. So you see this warm tongue that sticks out of the equatorial Pacific. And then there's this La Nina event that happens in, every so often. It's kind of quasi-periodic, so it doesn't have an exact periodicity to it, but happens every 3 to 7 years. You'll expect one El Nino or La Nina event. And so now we're looking at larger time scales, so 5 to 10 years in the case of the El Nino oscillations, and then heights of a kilometer or so, and then length scales of thousands of kilometers, because they do extend far out in the Pacific. So we're talking thousands of kilometers here. And then you have the large scale circulation of the ocean. So now we're like in this regime where you're talking about this whole global system of currents. And so the time scales, again, hundreds of thousands of years, and the length scales are also thousands of kilometers when we're talking about kind of these surface circulation or the overturning circulation of the ocean. Okay, so now this is looking at kind of with the global overturning circulation. So now we're at the very edge of this chart, the time scale spatial scale chart. So now we're looking at the entire globe, where time scales are like thousands of kilometers of the overturning circulation. And then the height is the entire head of the ocean, and length scales of tens of thousands of kilometers. So that's basically kind of an overview of like what all of the different processes that might be occurring, from like the smallest ones for molecular diffusion and other processes mixing, to internal waves, to kind of boundary currents and mesoscale eddies, to kind of this large scale spatial overturning circulation. I think I might skip this. And I might pause because I wonder if people had questions because I'm already at 42. Wow.
Any questions? Malloy, you did have a question earlier. Yeah, go on.
So thank you for the nice presentation.
Sure.
So Lele, so can you please go to the sea surface temperature distribution slide?
Mm-hmm. Oh, sorry. Where is this? This one?
Uh,
Or
yeah,
the global one?
global one, please.
All right. That's not it.
Okay.
Okay.
Hmm. So my question is here, like, do you think they follow any pattern? The like clouds are moving, right? Clouds are
Mm-hmm.
moving. So sea surface temperatures, it cannot move, just it can affect another molecule. And so there, have you ever seen any pattern like sea surface are increasing some places, and that's again it is moving some places? Is it possible?
Yeah, absolutely does. So, I mean, this is like a global average
Mhm,
across a bunch of different months, right? So this is like I'm exactly not sure like if this is a few month average or if this is a decadal average, but this is like the very long term average. So like you could expect like in longer terms,
mhm.
longer time scales. So we're looking at decadal averages that you would expect like this kind of like smooth. I'm not sure whose mic is on. But yeah, so on long-term averages, yeah, you see this kind of pattern, and then on smaller terms, on smaller time scales. So your question is like, do you see patterns when you're talking about
Like weather
exaggerating?
pattern, right? Scientists are working on the to detect the weather pattern. Like the weather models working good for 1 day prediction, like hot. So can we
Yeah,
predict like where the temperature will increase, where the temperature will decrease in the time being?
yeah, you can. So there are like forward-looking models for sea surface temperature also, but I mean, you have to like run a forward model that is integrated with the atmosphere and also that has like a coupled ocean model
Mhm,
component to it because like sea surface temperatures are not only they're not just determined by the the radiation that's coming in, right? Because you have
mhm,
air sea fluxes that happen, and you also have the dynamics that's associated with the atmosphere and the ocean. So it's like a coupled system. So this this figure over here on the left hand side is just kind of a simple average that this might explain kind of the long-term average, but if you're looking at, oh, I want to predict the sea surface temperature at a place tomorrow,
mhm,
then you have to like, maybe couple it with an atmospheric model, and then also a coupled ocean model because like not only will the radiation affect it, but there's also the dynamical part of it. I have kind of ignored it here just for this example, but
mhm.
if you're looking at small timescales, then you want to be able to be able to account for the dynamical part, which also affects sea surface temperatures on like smaller timescales. So yeah.
And another question. So nowadays, now I have seen in the like YouTube or in the Google, like some places, like scientists are using some chloride to make so the draining will happen there. So is it possible to control the temperature any places, certain places, like some places we need more temperature, like where growing trees and other things, and some
Uh-huh.
places we do not need temperature, we want to be cool, like where which place we are living, we
Yeah.
always want to like soothing weather. Is it possible to we can control in future like the temperature, because America is surrounded by the ocean, right?
Mm-hmm.
It's also depend on the ocean also, the weather and everything.
Mm-hmm.
Do you think is it possible like controlling the clouds, where the raining will happen, where the raining will not happen? Is it possible to control the temperature also?
Oh, that's an interesting question. I don't know. It's more geoengineering than oceanography, but to a certain extent, you can control the temperature. I suppose, like if you're doing cloud seeding experiments, then you
Yes,
might be
yes,
able
yes.
to, like, if you see the cloud, maybe there's rain or there's snow, depending on what the temperature is, then you
Mhm,
might be able to control it for like a little bit of time. But there's no like a thermostat, you can't really set the temperature to 72 degrees and then expect it to be 72 because it's always moving, right?
mhm,
So it's a dynamical thing. So you I'm not sure if you can do that because it's a fluid, right? So the ocean is a fluid and the atmosphere is a fluid. So
Mhm.
as soon as you set the temperature, suppose let's just give it that you set the temperature and where you are in Baltimore, right? So if you set the temperature there, then there's going to be a gradient in
Mhm.
temperature based upon you set it the temperature to 72 in Baltimore, but I guess in New York City it's 85 degrees. So then you have that gradient, and that gradient will, you know, the gradients don't exist in nature, so that gradient will have to be flattened out, and so there will be dynamics that's associated with that gradient, right?
Mhm.
So I don't think that it's possible to control the temperature on like long time scales, or I don't, this is a theoretical question. I don't even know if it's possible, but I doubt that it's possible. But
Okay.
yeah.
Okay. Thank you. Thank you for the
Sure.
reply.
And thanks, Malloy. I want to sneak in a question too.
Mm-hmm.
So from the beginning of this lecture, you've really highlighted a lot about the influence of temperature
Mm-hmm.
on oceanic behavior. And
Mm-hmm.
looking at the processes that you've been discussing that sort of have the impacts on the webs, whether surface or internal. My question to you is, the temperatures are highly concentrated in the equatorial regions versus the polar regions. Now,
Yeah.
can we, if you map those processes, right, to the polar regions versus the
Mm-hmm.
equatorial regions, do
Mm-hmm.
we see any significant differences in the impact, and where should we be concerned most? So, for example, if we look at where it's smaller processes, right,
Mm-hmm.
the motion processes in the beginning at the molecular level versus when it gets to the climate level or climate change level. So
Mm-hmm.
where is the most impact, could be the most impact in your opinion, when you look at it, mapping it to the equatorial versus the polar regions? I
No,
don't know
that's a
if the
good
question
question.
makes sense.
So yeah. So you're asking is like when you're considering smaller molecular processes versus
Mm-hmm,
large scale like
mm-hmm.
ocean currents and stuff,
Yes, please,
what
yeah.
is what is more impactful for.
Mm-hmm. These different regions, whether polar versus equatorial, where the temperatures are higher versus where they're lower.
Yeah, so I think maybe I didn't I probably didn't touch on it, but it's you have to like think of it in terms of a system of equations, and so
Mm-hmm.
all of the smaller scale processes are occurring in tandem with the large scale processes, right? So you're trying to, when you're looking at the climate system, like all of that turbulence and molecular viscosity and the large scale oceans currents and the overturning circulation of the ocean, all of that is happening in tandem. So while there is like different contributions of things uh, to the overall dynamics of the ocean, it's hard to like to pinpoint what is more important, what's not important, because it is all occurring all at the same time. And so when you're looking at the fluid motion, you have to like solve for all of it. So like those climate models and the ocean models and the weather prediction models, they're all doing all of that in tandem. So they're solving for the entire fluid dynamical equations or simplifying it as best that they can. But yeah, all of those are occurring simultaneously.
Thank you.
Okay, covered that. All right, so I kind of wanted to like, we have 10 minutes. Okay. Like briefly touch on so stuff that Dr. Zhang had covered, but kind of more in the context of the ocean. So I thought that that would be a good bridge between what I'm talking about and what he talked about. So you guys are already kind of familiar with the stuff that he discussed, which is kind of the global energy budget. And so, this is a very simple kind of schematic that you have this short wave radiation that the sun is bearing down upon us, and it's heating or cooling uh, the atmosphere, and then part of it gets to the ocean, some of it gets absorbed, and then there's outgoing long wave radiation that balances that out, right? And so there's a bunch of different processes that occur at the ocean surface or even at the bottom of the ocean or throughout the depth of the ocean. And so at the surface, you might expect evaporation, and other sensible heat fluxes that occur, and then there's the action of the wind and turbulence that occurs right at the surface. And so this is a kind of a very simplistic kind of schematic of what the heat flux is, or where the heat fluxes might be coming from. And so you could make that slightly more complicated. So what I said earlier, you have Q shortwave, which is the shortwave radiation from the sun, and then you have outgoing long wave radiation, so that's QILW, along with certain other evaporative fluxes. So you have latent heat fluxes and sensible heat fluxes that are also contributing to the long wave radiation. And so it's this balance between the short wave and the long wave radiation that basically sets the heat flux budget at the surface of the ocean. Okay, so this is kind of similar to what Dr. Zhang was discussing, but so I kind of wanted to just turn it back to heat fluxes for a bit. So we're trying to calculate what the net heat fluxes at the ocean surface are going to be. So this diagram is basically telling you that there's 100%, say, that's coming in from shortwave radiation. Some of that gets absorbed in clouds and in the atmosphere, and then some of that makes it down to the surface. So that's the surface shortwave radiation that the ocean surface absorbs, and then some of that then is reflected back as well. And then there's long wave radiation that's emitted from the surface of the Earth. And for the surface of the Earth, we're just considering the ocean at the moment. And so you've got shortwave and long wave radiation. Those are the radiative terms that Dr. Zhang had covered. And then there's some turbulent heat flux terms. So there's the latent heat flux, and then there's sensible heat flux. So both of these fluxes are also contributors to the surface energy balance. And so again, so we don't have to necessarily spend too much time on this, but then shortwave is just radiation coming down from the surface, or sorry, from the sun, and some of that makes it to the surface of the oceans, that Q sub S. And then long wave radiation is outgoing radiation that leaves the surface of the Earth. And then you have some turbulent heat losses that are due to evaporative cooling. And so you can imagine that the surface of the ocean is also cooling off because it's evaporating, right? So that those are turbulent heat fluxes or latent heat fluxes that contribute to the evaporation of the surface ocean, and that results in the cooling of the surface. And then there's sensible heat fluxes that are just happening at just the air-sea interface. So it can heat or cool the surface depending on the processes involved, but those are generally quite small. And so that's basically the balance. So if you want to calculate what the surface heat fluxes are, you can just add all of these terms together, and then you'll get what the surface heat fluxes look like. And so this is basically looking at the ocean. I've just kind of partitioned this out into radiative fluxes, which are the long wave and short wave radiation, and then the turbulent heat fluxes. And so what you see in the short wave radiation, again, this is basically dominated by this spherical nature of the Earth. And so at the equatorial regions, you have more shortwave radiation, so you would probably expect more heat to persist in the system in shortwave radiation near the equator. And then as you move polewards, you have less shortwave radiation because of kind of the tilt of the Earth, and also the spherical nature of the Earth. And looking at long wave radiation, again, this is more or less consistent. You can see all the contours are about 50 watts per meter squared. So there's not much of a variation when it comes to kind of the global picture when it comes to long wave. Latent heat fluxes. So these are basically evaporative cooling related fluxes. So you have more evaporative cooling in some areas, less evaporative cooling in other areas. And that kind of depends on where the ocean currents are as well. And so that's kind of a chicken and egg problem, I suppose. So where are the ocean currents, and how does that affect surface heat fluxes and latent heat fluxes? And then sensible heat fluxes, like I said, they're quite small, but they generally occur in very stormy regions, or regions that have really strong boundary currents. So you'll see that in the kind of the Gulf Stream or the off the coast of Japan, maybe due to another strong boundary current there. And then you see like some turbulent heat fluxes off the coast, I guess in the Southern Ocean in certain areas that are that occur due to like big Southern Ocean storms that happen. And so this is basically all the different components, and you can look at what the seasonality of it is. So you can add all these terms up and like look at what the winter heat flux, for example, looks like. So you could imagine that in the winter you have surface heat fluxes that are negative, and so you're losing heat in the winter time. And then in the southern hemisphere, that's the opposite because they have summertime there in the winter in northern hemisphere. And the reverse happens in the northern hemisphere summer, where you have like the total surface heat fluxes are positive in the northern hemisphere versus negative in the southern hemisphere. But what you can also do is basically average this out for the whole year. And so now this is a picture looking at the average annual surface heat flux. And so what I've done is basically take all of those heat fluxes, so the latent heat flux and the long wave and short wave radiative fluxes, and average them together, and this is the kind of the picture that you get. And so you have the surface heat flux, and so the positive is that the ocean is getting heated there. So you have a positive surface heat flux in certain areas, and then in regions of boundary currents, so like the Gulf Stream and the Kuroshio, which is off the coast of Japan, you have kind of a loss of heat, and so you have this like pattern of heat flux. And so this pattern, I mean, why is this pattern of surface differential surface heating can't really exist without nature trying to equilibrate, right? So you can't have a net heating or a net loss of heat perpetually. So physically that would be impossible, right? So there's something that's got to happen. So you have net cooling here and net heating in these areas, and that will cause something to happen, right? So you would have motion of water, and that's why you have like kind of surface currents. And so I'm not sure if I have time to cover that, but maybe I'll do a couple more slides and call it. Josephine, I don't know. I'm getting to 5
Yes,
o'clock.
please. Sure enough. Go on.
Okay, so all right. So what I was saying was that you could these are the average heat flux components: short wave, long wave, latent heat, and sensible heat at the surface. What you can do is calculate a zonal average. So you can average across each longitude in space. So what you can do is compute this zonal average. And so now when you've taken the average, this is kind of what the plot looks like. So you have, this is latitude. So this is Southern Ocean. This is kind of Arctic, and the equator is in the middle. And so you have all of these different fluxes now. So you have shortwave flux. So like I said, shortwave flux is maximal at the equatorial regions, and then it decreases down and as you go northward or southward. Long wave flux, again, it's mostly constant, but it's black body radiation. So if you have higher temperatures, it's going to radiate a little bit more. So again, it's more correlated with the temperature of the water. So again, there's not much of a pattern, but yeah, it's more equatorially dominated. And then you have sensible heat fluxes, which is basically kind of zero for the most part, and then you have some latent heat fluxes, right? So, and then you can add all these fluxes together, and you can see what the net flux looks like. And so this is the net heat flux across the globe when you're looking at kind of a zonally average picture. So you have net heat, positive heat fluxes near the equator, and then some negative heat fluxes away from the poles. And what's the reason I'm showing you this? And so I'm just going to quickly march along and just kind of show you the point of this, is that nature will not allow these heat fluxes to exist in this way. Like you can't have a net gain of heat in certain areas of the ocean and a net loss of heat in other areas of the ocean. Like these areas in the equator will continue to get warm, and then these areas in the polar regions are going to continue to lose heat, right? So then then that's not going to be sustainable physically. So what you can do is calculate the ocean heat transport, because the ocean is a great conveyor of heat. And so what you can do is basically integrate the net heat transport from the Southern Ocean all the way northward. So what I'm doing is basically integrating the net heat flux from the south all the way to the north. And so when I do that, I get this. So this is the net northward heat transport when I do this for the entire ocean. And so this is in petawatts. So like if I were to start integrating this black curve northward, everything is basically close to zero, and then I'm moving north, it's still negative, and then it's a little positive, and so I'm still seeing that fluctuation here. And then it's all still negative, I'm still integrating. And then when I reach the equator, then suddenly this stuff starts to go back up positive. And so that's what you see in the net northward heat transport. And then you keep integrating, and then you reach the kind of the northern hemisphere pole. And so what this figure is basically telling you that there's northward heat transport peaking at 30 degrees north roughly, and then it decreases. And so that 30 degrees north is basically corresponding to all of those boundary currents. So the Gulf Stream, why this is important is because it's transporting a bunch of heat from the equatorial regions that are very, very warm to the poles. And so my whole point of showing you this was that you can't have a system where you are accumulating heat in one part of the ocean and you're taking away heat in the other part of the ocean, because the dynamical system that the Earth system is, like you'll have atmosphere and the ocean both going to try and transport that heat from areas that have a surplus of heat to areas that have a deficit of heat. And so that's basically what the northward transport looks like. And so this is just another kind of picture of what the Gulf Stream looks like. Again, so this is going to start coloring. So you have sea surface temperatures that are warmer near the coast of Florida. And so as you move northward, you have basically this northward heat transport that's occurring because of these currents. And so the reason that these surface currents and other ocean currents exist is to do exactly this, because our Earth system is set up in such a way that there's differential heating, there's differences in all sorts of properties. And so ocean currents act as another way to transport heat. And so another picture is you can look at the global picture. So now, instead of just looking at the Gulf Stream, you can animate what the surface currents are doing when you're looking at a sea surface temperature map. And so again, like you have warmer temperatures in the tropical regions and colder temperatures in the polar regions, but what the currents are doing is transporting this heat northward and southward, depending on what hemisphere you're in. So yeah, I think I should stop there, and then yeah.
Thank you
Take
so
some.
much, Ratnaksha. I know there were
Sure.
hands raised a bit after that, but because
Oh,
of
I didn't really
time, yeah,
notice.
no, it's okay. Because of the interest of time, we'll just stop here. And we'll definitely, folks can reach out to you with questions. This
Okay.
was very, very insightful. I know you had a lot to cover. Probably need a
Yeah.
couple more lectures, right? So we want to appreciate everyone's time for joining us in our second workshop for the Polar Series. And we look forward to the next one coming. Thank you again, Dr. Ratnaksha.
Sure, no problem.
Have a good one, everybody.
See ya.
Thank you for the presentation, Dr. Lele. Bye. Bye, Dr. Susmi.
Bye.